Okay, based on what we saw in our previous video, we now understand that to transport traffic information for AI applications in Layer 3 environments and achieve the desired job completion time, we need to use Rocky version 2. However, there is something else that we must also guarantee. And here I will introduce a new requirement that we call lossless networking, which means that we must guarantee a level of data transmission that does not suffer from packet loss, since in Rocky version 2 we will not perform retransmissions. And you might be wondering, how can we prevent packets from being dropped in transmissions in environments where traffic volumes and bandwidth demands are growing exponentially every moment? Well, this is where we need to rely on quality of service functionalities that allow us to control traffic and anticipate all the symptoms that appear before the switch or the end device has to start dropping packets, such as collisions, interface or buffer congestions, lack of synchronizations between sender and receiver in terms of frame sizes, data transmission frequencies, etc. In this video, I'm going to focus on one of these quality of service features that we have available in this process, known as Explicit Congestion Notification or ECN, as defined in RFC 3168. For this, we need two components. Endpoints that support ECN, meaning they can assign and read the ECN indicators in the frame headers, and a network that supports ECN, meaning it writes the ECN indicators into the frames. Let's remember that ECN indicators are written in the IP header. If you haven't seen the previous published RDMA and Rocky version 2 video, I encourage you to watch it. The ECN indicators are as follows. 0x00 indicates non-ECN capable. 0x10 indicates ECN capable transport 0. 0x01 indicates ECN capable transport 1. 0x11 indicates congestion encountered. However, assigning these indicators also required proper analysis. So ECN uses congestion avoidance algorithms to check the volume of traffic being transmitted and perform the corresponding marking, such as the algorithm used by the Cisco Nexus platform called Weighted Random Early Detection, or WRED, which now I'll describe. In Nexus, WRED is used in a per queue mode. It means that manages network congestion by separating traffic flows into independent queues. In these queues, we will define two thresholds. The lower threshold, which we will represent in yellow, and the upper threshold, which we will represent in red. As buffer utilization increases and reaches the yellow threshold, a certain number of packets leaving the queue will be marked. The number of packets marked depends on the packet drop probability defined in WRED for this threshold. For example, in Cisco, it represents a percentage of all outgoing packets. That is, if the yellow indicator is set to 10, 10% of the packets will be marked. If it doesn't clear the buffer and the queue continues to fill up, we might reach the red limit, in which case all packets are marked. But let's remember that the goal is not to discard packets. On the contrary, the goal is to avoid packets lost to achieve a lossless network. Therefore, we will use the WRED algorithm with ECN to obtain a better result. In this example, we will use nodes A and B and assume that both are compatible with ECN. Node A will constantly send information to Node B. By using quality of service, we will place queues on the Nexus devices to control data traffic. If there are no congestion issues, the packets will be marked by the endpoints with the indicators 0x01 and 0x10 to confirm that the traffic is flowing smoothly. Let's assume that data traffic intensifies and one of the queues reaches its yellow threshold. In this case, the Nexus switch, instead of dropping the packet, will set the identifier to 0x11 in a percentage of the packets, as defined in wred, so that the node understands that congestion is beginning. After node B receives the packet with the header 0x11, it understands that congestion is occurring and generates a congestion notification packets (CNP) and sends it to node A, which is the node from which it received the packet that is now marked. Since only some of the packets were marked, node A reduces the flow of data and continues sending packets. However, if congestion increases and the red threshold is reached, all packets will be marked, triggering more CNP packets from node B to node A. Consequently, node A will have to drastically reduce the transmission rate across all its flows to node B to prevent packet loss. Consequently, node A will have to drastically reduce the transmission rate across all its flows to node B to prevent packet loss. This should alleviate the congestion and allow the buffers to clear, after which node A's data transmission rates to node B can be increased again. In this way, we have a level of flow control in Rocky version 2 data that allow us to move towards the goal of a lossless network. However, there are other features that we can use in conjunction with ECN to achieve this goal, but we will talk about that in our upcoming videos.